All right, we're going to continue with chapter 16 today. And then when we do acids and bases, let's just stick with acids for right now. If we look at strong acids, what we're going to see is that the Ka, the acid hydrolysis constant, we call it, is going to be very large. When K is very large, then we just assume the reaction goes 100%. And so an example that we saw earlier, something like HCl. HCl has a Ka that's very large, and so the reaction here in hydrolysis, H2O liquid, is going to go to H3O plus chloride. But for this, we'll just say it's 100% forward, so it just goes one way, a one-way reaction. One-way reaction. For weak acids, we have, Kas that are small. And what this means is that we're going to have partial hydrolysis. And so when the reaction goes 100%, we can say that this is the percent ionization here. And so we would say 100% ionization, though this is a hydrolysis reaction that we're looking at. When we have partial hydrolysis, an example would be acetic acid here, plus H2O liquid. Then we look at the K value for this, and it isn't so big. The Ka for this reaction is 1.8 times 10 to the minus 5. Yeah. And so what this translates into is it translates into about 0.1% hydrolysis slash 0.1%, roughly ionization. And so for acids, we often use the term ionization. And so the stronger the acid, the higher the percent reaction is, or percent hydrolysis, or percent ionization. Actually, they're all the same, 0.1% reaction, which is the same as hydrolysis, which is the same as ionization for this particular reaction. And so the stronger the acid, the greater the percent ionization. And so we take a look at the K values. In the book, and let's just take a look at the range of the K values here. Bring that up. So what we're going to do is we're going to look what happens when an acid is in water. These are all multiple equilibria problems because, not only do we have the acid with a Ka, but we also have water with a Kw. And so we'll deal with that. Hopefully we can solve it in a stepwise fashion, because if we can't solve it in a stepwise fashion, then we have to solve it together, which is simultaneous system of equations.
That's about.
Mm-hmm.
Sometimes I can't find the multiple equilibrium example in the book.
You couldn't find a multiple equilibria problem? All of chapter 16 is multiple equilibria.
I know, but I don't see an example of they doing that.
Simultaneous.
Oh, simultaneous?
And stepwise.
And stepwise? That's because in the book they just focus on stepwise. They try to solve all problems stepwise, but it fails. It fails sometimes, and we'll take a look. I'll show you. All right, so let's take a look at some of the Kas. This is from Appendix D. So here we see acetic acid is 1.8 times 10 to the minus 5. It's a weak acid. But 10 to the minus 5, 10 to the minus 12, you know, for monohydrogen arsenate, which is 10 to the minus 12 is very weak. 10 to the minus 10, 10 to the minus 11, 10 to the minus 3. So what's the biggest one that we see?
So minus 2.
10 to the minus 2.
1.1 times 12. Yeah, probably minus 2.
Oh, here's 10 to the minus 1. Trichloroacetic acid, 10 to the minus 1. Some people group trichloroacetic acid with the strong acids. Actually, it's fairly large. 0.3 is Ka. So it generates a significant amount, but it's not like 100%. You know, so we're going to get a lot of hydronium here. So trichloro, no, like sulfuric acid, there's no Ka value there. It always gets me during the exam on chapter 16, somebody always comes up and asks me, you know, you didn't give me the K value for sulfuric, or you didn't give me the K value for hydrochloric, or you didn't give me the K value for nitric acid. They can't solve the problem.
Why is selenic acid a strong acid?
You know, the why?
It's not on our 7.
It's not on your 7, but you know, it's not the 7 strong acids of the universe. It's the 7 common strong acids, and selenic acid is not common, so that's why it's not on your list. There's actually the 7. There are a lot more strong acids than 7. You know, and it's just useful memorizing those 7. And then there's super acids too. And so selenic acid, why we want to dig into that. We want to look at the structure and how that affects the properties. So structurally, selenic acid and sulfuric acid must be similar, which you would expect since they're in the same family. Selenium's right under sulfur. However, selenic acid is strong acid, and others. And so we see, wow, check this out. This is you heard of triprotic acid? You know what triprotic acid is?
I can give more than 1 hydrogen.
It has 3 hydrogens, 3 acidic. What is this? Pyrophosphoric acid. The tetraprotic acid. So, you don't often see tetraprotic acid. Phosphoric is very common, triprotic acid. Citric is a common triprotic acid. These have 3 acidic hydrogens. And they lose them stepwise. Same thing with phosphoric, hydrogen 1. But take a look at the successive ionizations here. 10 to the minus 3 for the first one, which means the first one comes off fairly easy. The second one, 10 to the minus 8. Not much ionization there, probably. And then the last one, 10 to the minus 13, so minimal ionization in water. Did we talk about phosphoric acid last time?
I think we did.
A little bit. And so I was looking around here, 10 to the minus 1 here, iodic acid, 10 to the minus 1, it's fairly strong. As far as on the weak end of things, we did hydrocyanic acid. Hydrocyanic acid is not a very strong acid. Where is that? Here. I mean, 10 to the minus 10, that's pretty weak, right? That being weak at low concentration, you'd expect a lot of hydronium to come from water. here. There's some that are unusual. In this case, look at this one here, HS minus, the hydrogen sulfide ion, 10 to the minus 19. 10 to the minus 19 is actually smaller than water. You know, water is 10 to the minus 14 for the hydrolysis of water, that is the ionization. And so this is actually a weaker acid than water. This will play into our stepwise the way we solve things stepwise. So let's take a look at how we deal.
Is there oxalic in there?
Yeah, oxalic is pretty strong. This is just alphabetical, so I'm going to scroll left here.
It's on the right.
Yeah. Oxalic is 5.4 times 10 to the minus 2 for the first hydrogen, and the second one's 10 to the minus 5. Both of them are pretty good. Here. All right, and so let's take a look at dealing with some acids in water. You know, for monoprotic acids, we only have, you know, Ka and Kw to deal with. You know, for polyprotic acids, we have more. So monoprotic, we just deal with these two equilibria. Polyprotic, we're going to have Ka1, Ka2, depends, ... and Kw. So we're going to have quite a few equilibria happening at the same time. Then we deal with strong acids and weak acids too. And so it doesn't matter, we treat all of them the same. You know, we try to solve these stepwise. If each successive step step does not perturb the previous, then okay. If it does perturb, then must solve simultaneously. And so the question comes off, why not combine? And so the three techniques that we're going to use to solve multiple equilibria are going to be stepwise, well, actually, let's do stepwise, combined, and simultaneous. Simultaneous works for everything.
It's about the same.
Yeah. I mean, this is the way we're supposed to solve it, because everything else is making assumptions, which leads to a small error or maybe a significant error in the calculation. Stepwise works, you know, in general, this works if the Kas become successively smaller by orders of magnitude. And so if you see something like this sequence, 10 to the minus 3, 10 to the minus 8, 10 to the minus 13, this should work stepwise because each K gets considerably smaller, so each successive step becomes less and less significant, right, in the overall. Just the first step has the biggest impact, and then each successive step is a small addition to that. When the successive Ks, actually, let's do this one. let's look at an acid in here where it might not work as well, or it might work. You know, if you look at citric acid, the first step is 10 to the minus 4, this next step is 10 to the minus 5. It's pretty close. When you have K values, and in fact there are K values with the same order of magnitude for both acidic hydrogens. I have to look in this table again, but I have to find that. What was that? Maybe it's not here. Oh, here. No, all these are pretty well behaved. The one where I got the K's that are very close together, you know, the K's that are very close together, you know, then that means step 2 would have a significant impact, you know, since both of them have about the same impact if the K values are close. Take a look at the practice exam. I think I threw it on that. Perhaps. Or maybe it was a previous year's exam.
Did you just post chapter 16?
No, I haven't. I'll post that. Chapter 16. And so if the K values are somewhat close, then you know, they're both going to have about the same impact, which means it's most likely going to be simultaneous. But if the, you know, this is the way we like to think about it. Like, you know, K for step 1 is much greater than K for step 2, which is much greater than K for step 3, then et cetera. That's going to check out good. But if K for step 1 and K for step 2 are pretty close together, then most likely it's going to be simultaneous. So stepwise works for certain cases, actually most cases, because when you look at most of these acids, that's the case, right? So this is why the book in chapter 16 is going to focus on stepwise. Right, and then if I dig around, I can find an acid where, you know, the two Ks are quite close to each other, and then it fails. Right? Combined, this works for certain scenarios. This is going to be in chapter 18. Yeah. It only works when very specific conditions are met. It doesn't work here. And let's take a look at something like phosphoric acid. Phosphoric acid is a triprotic acid, so H3PO4. So what we're going to have is we want to go in from biggest K to smallest K, so stepwise. You start off with the biggest K, and then you go down to the smallest K. Biggest K should have the most significant contribution of hydronium to this. And since we're dealing with, this is an acid, you know, this is acid. So what we do is we look for all hydronium producers. And so hydronium producing steps. And so, well, the biggest K is going to contribute the most hydronium. The biggest K is going to be this one, 7.21 times 10 to the minus 3. Water is only 10 to the minus 14, so water is not going to produce nearly as much hydronium. And so here, we'll say this is step 1. Step 1 is going to be phosphoric acid, H3PO4 plus H2O liquid. This is going to go to hydronium plus dihydrogen phosphate. This is a Ka1, or excuse me, step 1. So we'll just call it Ka. Actually, what we could do is we could call it Ka1 for the first step of phosphoric acid, H3PO4. And this is equal to Ka for phosphoric acid, H3PO4, which is 7.1 times 10 to the minus 3. And then if we go to step two would be the second proton breaking off. All three protons do not break off at the same time. You know, we got to have a collision to break each one off. And this is going to generate hydronium plus monohydrogen phosphate. We call this Ka2 for phosphoric acid, the second step in the hydrolysis, or Ka for the dihydrogen phosphate ion. They're both the same thing. Okay, the next step, step 3, is going to be monohydrogen phosphate, hydrolyzing water. This is going to produce hydronium plus phosphate ion. This is Ka3, phosphoric is equal to Ka for monohydrogen phosphate. This is 4.2 times 10 to the minus 13, which makes it just slightly bigger than water. And so water's got to be the least significant contributor to hydronium to this acid solution, and that would be the autoionization. This or the acid hydrolysis of water to form hydronium and its conjugate base, hydroxide. This is Kw. Well, some people say, why don't we just combine steps 1 through 3? You know, remember Hess's law analogy, or whatever they call it, for this? So why not combine these three? Why not combine? So if I add up these three equations, what do I do with the k's? Multiply them, and so that's easy to do. And so if we combine those three, let me add up the equations. A whole bunch of stuff cancels out as spectators. So I'll have an H3PO4 plus 3 waters. This is going to give me 3 hydroniums plus a phosphate. And the K for the combined is just going to equal Ka1 times Ka2 times Ka3. We learned this in chapter 15, right? This is how you determine Ks without actually having to do an experiment. And so this is a perfectly legitimate question to ask. We should be able to just combine the three, and then, you know, we've just saved ourselves a lot of work, right? We saved ourselves a lot of work, but we're going to get the wrong answer. And the reason we're going to get the wrong answer is not so apparent here. This is why the combined method only works for certain scenarios. It only works for certain scenarios because in terms of, you know, mass balance problem. We have a mass balance problem. You've heard of conservation of mass, right? Conservation of mass basically says that atoms are neither created nor destroyed. Well, basically a whole bunch of, not atoms, but a whole bunch of species have disappeared from this. Some important species are missing. Important species, let's just say, are missing. They haven't disappeared. Which, well, you know, right, H2PO4 minus is missing from this. And if we think about it, the first step is the most significant because the K is the biggest, you know, here. And each successive step gets smaller and smaller. And so that means there should be minimal phosphate present at equilibrium because it's 3 steps down. And that means that most of the phosphorus from phosphoric acid actually should end up staying as phosphoric acid, but you know, the species that should be present after that. I'd say maybe this is the most abundant, followed by H2PO4 minus. H2PO4 minus should be way more abundant than phosphate. And so, you know, what happened to important species are missing? What happened to H2PO4 minus and HPO4 minus, 2 minus? What happened to those? And so this is making a faulty assumption. When we say this, we're saying that all the phosphorus, in phosphoric acid, when it hydrolyzes, goes into only one species, phosphate. And so there's a mass balance problem here. We know that these other species exist in significant quantity, are more significant at least than phosphate, but they aren't shown. Okay. Does that make sense? And so we are not going to use combined method in chapter 16 and chapter 17. When we get to chapter 18, then we'll see under special case that those intermediate species have a negligible concentration, therefore we can ignore them. But so important species, what happened to this? So can't use combined. So it's either stepwise or simultaneous, and I think this is going to work stepwise. Let's just try to figure it out. Whether it's monoprotic or polyprotic, it's always the same approach. We just start off with the biggest K. And so let's say we have a beaker that's labeled. Let's go with 0.100 molar phosphoric acid. I like 0.100 molar because it's easy to calculate the percent reaction or percent ionization. So if we start off with 0.100 molar phosphoric acid, then for step 1, we'll just take the biggest K, which will be this one, and then just solve it using ice. What we're going to say is initially everything's reset to the left, right? Initially we have no collisions with water, and we have 0 hydronium and 0 dihydrogen phosphate present. This is the easiest because we don't know, how much of the other species are present at equilibrium, so it's best just to assume equilibrium hasn't been established. And we're starting off with that. K for this was 7.1 times 10 to the minus 3, which is going to equal the hydronium ion concentration times the dihydrogen phosphate divided by the phosphoric acid. It's a weak acid, so most of it would stay as phosphoric acid molecules. But we're going to lose some. That amount we lose is minus X, and then we'll have plus X and plus X.
Ice table.
The ice table, right. And then we're going to have 0.100 minus X, X, and X. And then we just plug it in here, so we're going to get X squared over 0.100 minus X. And then I just always try the simplifying assumption. If it fails, it fails. But might as well just try it. We're going to get X squared over 0.100.
Oh yeah, on the test, I tried simplifying assumptions on one of the problems. They gave me a negative quantity, so it fails. Like I got 23 at the end, but then the solution is just 0.100 molar.
Yeah.
And
Yeah, if it fails, then you've got to try some other method. We'll see if this
I ended up using
fails.
the quadratic formula, but that also fails.
All right, well, let's see how it works on this one, the simplifying assumption, if it fails or if it's successful. Can someone just calculate this? 7.1 times 10 minus 2 square root. 0.0266. And so, you know, with 0.100, then we see it's a 26.6% change, which is a fail.
Fail.
This one failed too, unfortunately. So we can't do that. So we have to use the quadratic. So let's go ahead and get this into quadratic form, which is x squared. And so this is going to be minus, so we'll do plus 7.1 times 10 to the minus 3x minus 0.100 is equal
Oh
to
yeah, I
0.
tried that on a big K and I got really messy numbers.
Well,
If K is like equal like 190 for example, and when I do the quadratic, I get really messy numbers.
yeah, that's why having a calculator that solves quadratic is very nice, because all you have to do is you plug in. Does anybody have a quadratic solver calculator? No? All right. Well, if you don't, this is what you could do. I do this when I don't have my calculator. I just go to a site. You can't do this, of course. You're going to have to do this on.
You can't have access to his military base. Right, Sam?
Unfortunately, you aren't going to be able to do. Oh, I don't want this. I just want the simple solver. Where is it? Unfortunately, you can't do this on the test, of course. No, you're going to have to do it, or you're going to have to break down and buy one.
It's gotta be, you gotta multiply. Yeah, you have to multiply, but it's point X.
Oops, you're right. I forgot.
That's just, it's minus.
Oh, did I? 7.1 times 10 minus. I forgot that. So it's 7.1 times 10 to the minus 4. Thanks. We would have caught that on the double check. What is NaN? Oh, there. Okay. We get two. We get this one, negative, which it can't be negative. It can't be negative. So it's got to be this one, 0.0233. So x equals 0.0233. You know, if you like solving quadratics by hand,
I didn't
I
get
don't.
the right answer at the army. I didn't.
well, let's see if this is the right answer. We always do our double check. So the hydronium ion concentration is 0.0233. In other words, this is 23.33% ionized, right? And so, you know, phosphoric is a pretty decent acid. I mean, a quarter of it's ionized. So minus 0.0233, which is going to give us 0.0767 molar. And so 76.7% remains unionized on average, and about 23.3% ionized here. This one I'm not going to box, but this, you know, this dihydrogen phosphate was 0.0233 molar. And, you know, the combined method completely ignores that, right? Although, you know, these ones are tricky. I shouldn't really box these because these ones are going to be carried down to step 2. This one stops here, so I'll double box it. But this one goes down to step 2, and this one goes down to step 2.
So you said that 7.6% ionized?
No,
76.
no, 76.7% unionized, 23.3% ionized. And so in this beaker, we're going to have about 0.0767 molar phosphoric acid molecules. You know, it's a dynamic equilibrium, so this process of exchange processes occurring. So now when we go to step 2, it's the dihydrogen phosphate plus water. You're going to go to hydronium plus monohydrogen phosphate. All right, from step 2, we get our dihydrogen phosphate concentration, which is 0.0233 molar. For stepwise to work, let's double check this equilibrium and make sure that the K checks out first. Forgot to do that before we do the next calculation, in case I made a mistake. H2PO4 minus.
Hey,
And 2 minus.
Did the quadratic formula method ever fail? I know, but on the test, I didn't get the right answer. I was like far off. I got like 1,000 something when K was like 190.
Sometimes when people don't reset, then it could fail because it's not that the quadratic formula fails, it's that your calculator failed because it can't carry enough digits. But can somebody just check this? 0.0233 squared divided by 0.0767?
It works.
It works? All right. It comes out to what? What does it come out to? 7.1? I'm just curious about round off. What does
7.1 and 7.07.
7.07, okay. 7.07 times 10 to the minus 3, which is, that's good, just rounds. Not, obviously it should be exactly the same, but we didn't carry all our digits, right? We dropped a bunch of digits. So we ought to, right, that's close. And so this one, from step 1, we get this much, but we also get hydronium too, and we can't forget about the hydronium because there's going to be hydronium present from step 1, which is 0.0233 molar. What we're going to do is we're going to reset step 2. There's been no collisions yet, and so we just imagined this hasn't happened, and now we're going to let it happen. And so the change here is this. Now we have 2 things that are going to tell me this change is going to be small. The first thing is the K. We're going from 10 to the minus 3 to a K value of 10 to the minus 7. Oh no, sorry. Yeah, 2.1 times 10 to the minus 7. And so K's orders of magnitude smaller, 2.1 times 10 to the minus 7.
It's 6.3 times 10 to the negative 8.
Oh, sorry. Thanks. 6.3 times 10 to the minus 8, which is even better. That's 5 orders of magnitude roughly, right? And so, number 1, the K is a lot smaller. And then number 2 is the common ion effect. The common ion effect is this. What we call this, one common ion between step 1 and step 2 is hydronium. When we have a lot of hydronium present here, are we going to generate much monohydrogen phosphate? No, because this hydronium will attack the monohydrogen phosphate as it's being formed here. And so this is like that predator-prey analogy. If the fields were empty, and then we could populate those fields with hydronium and monohydrogen phosphate, but the fields have this predator, which is the hydronium, which is going to attack the monohydrogen phosphate as it's being formed, which means that the plus X here and the plus X here are going to be even smaller than what would be expected from the K because of the common ion effect.
Well, why would not much monohydrogen phosphate form? Like, how do you know the one is attacking one another?
Well, the other way to think about this is when you look at the K expression, which is going to be the hydronium ion concentration times monohydrogen phosphate divided by the dihydrogen phosphate concentration. When we look at the equilibrium concentrations, 0.0233 minus X molar, 0.0233 plus X molar, and X molar. Just purely from a math point of view, we have 0.0233 plus x times x in the numerator. If there was no common ion, this would be 0 plus x. And since we already have this 0.0233 present here, x doesn't have to be as big to satisfy the equation. And so just from a math point of view, it's going to be smaller. Okay. But what's happening here is, this is just chemical reaction. The higher the concentrations of products here, the more it's going to favor the reverse because you get more collisions. More collisions means more reaction. Well, the situation here is this. If x is too big, what's going to happen? If x is too big, that's going to change the dihydrogen phosphate and the hydronium concentration significantly, which means that step 1 gets screwed up. We get this, endless loop. Because if step 2 screws up step 1, we can go back and fix it, but it's going to screw up step 2. And we can't solve these separately. We have to solve them simultaneously. So let's hope we don't have to solve these simultaneously. But I'm telling you, this one's looking good based on that, the K values. This impacts how we do the simplifying assumption. Some people were asking me about this rule of 100. The rule of 100 or the rule of 1,000. In our book, it's 1,000. I guess what was the video or something? Somebody was telling me a YouTube video. I haven't seen it. Oh yeah, okay. Kelly was telling me about that. But that works. The common ion changes the rule. If you have common ion, the rule's different. And so rather than giving you a separate rule for common ion, I just don't even bother with the rule of 100 or the rule of 1,000 because that rule might fail and this still works. So let's just go ahead and try it. If I try the simplifying assumption, I'm going to get 0.0233 plus x, which is going to be 0.0233. 0.0233 minus x will be 0.0233 times x. And therefore, x is equal to 6.3 times 10 to the minus 8. Okay, so let's justify that. We'll look at the percent change. The percent change is going to be 6.3 times 10 to the minus 8 divided by 0.0233 times 100%. And
That's going to be really big.
No, actually 10 to the minus 8 divided by about 10 to the minus 2 or so, give you about 10 to the minus 6 times 10 squared is 10 to the minus 4. It's going to be really small. Okay. Well, what does it come out to? 2.7 times 10 to the minus 4% is no problem. That's a great, if you see a percent change like that, then this is really good. This simplifying assumption worked really well. And so that's good for us because we go 0.0233 minus x is going to be 0.0. I need 7 zeros. So 1, 2, 3, 4, 5, 6, 7, and then a 6, 3. So let's tack on some more zeros here. And then we'll do the subtraction. So this is going to go to 0.0223, and then we'll go to, oops. Okay. We'll do it this way: 7, 3, 9, 9, 9, 2, 2, 2, 0. I don't know if you want to carry that many digits. Actually, no, just leave it. Did it change much? No, barely changed at all. The same thing here. This is 0.023300 whatever plus 0.123456763. 0.023 So 3, 1, 2, 3, 6, 3. And then this is going to be 6.3 times 10 minus 8 more. I'll leave that one in scientific notation. And so this is what we mean by the next step does not perturb the previous step, because here, you know, did it really change? No. And then over here didn't really change, and so we're good. This, you know, does not perturb step 1. And so this did not perturb. Step 2 did not perturb step 1.
Wait, how do you know this doesn't change? That one over there.
Because if we plug in these numbers here and then recalculate K, it's going to come out the same.
Okay.
And so that means stepwise is good. Now it'll be obvious if it does perturb, because there are going to be significant changes here. The significant changes here, then it's going to perturb step 1, and then you're going to stop there and say that you have to solve this simultaneously. All right, so this is going to be the end of the line for dihydrogen phosphates. Our final dihydrogen phosphate concentration is this. You know, we generated some dihydrogen phosphate in step 1, and then we used up a tiny fraction of this dihydrogen phosphate for step 2. And so this will be the final concentration here. However, for hydronium and monohydrogen phosphate, we're going to get additional monohydrogen phosphate. Not additional. We're going to lose a little bit of monohydrogen phosphate to generate some additional hydronium in step 3. So let's go ahead to the next step. You know, if we're interested in a pH, did step 2 really change the pH at all? If you were to do a pH calculation, which is a negative log of the hydronium, no, you know, the pH is going to be the same. And therefore, for polyprotic acids, you usually just use step 1. If you're only interested in pH, you don't have to do 4 steps. Because what do you think? In step 3, are we going to generate much more hydronium? Yeah, it's going to be even smaller. And therefore, you could save yourself a lot of time. And so let's write that as a little side note here. On the side. For pH calculations, step 1 is usually adequate. Unless step 2 has a fairly large K. Like HSO4 minus. Let's look at sulfuric acid for a second. If we look at sulfuric acid, step 1, obviously you're going to get most of the hydronium from step 1. You know, this is a strong acid, so it's going to ionize 100%. But if you look at step 2, look at the magnitude of the K value here. Yeah, it's 10 to the minus 2. 1.1 times 10 to the minus 2. 10 to the minus 2, that's a heck of a lot stronger than acetic acid, right? That's like what is that? That's 3 orders of magnitude stronger than acetic acid. And this is just HSO4 minus. And so for something like sulfuric acid, you have to do step 2. Otherwise, you're going to miss about 10% of the hydronium in the solution. But when we look at something like phosphoric acid, no big deal. Or even sulfurous. Let's compare sulfuric with sulfurous. If I look at sulfurous acid here, you know, step 1 is going to be the most hydronium at 10 to the minus 2. I'm going to generate significant hydronium. But if I look at step 2, that's 10 to the minus 8. If I'm doing a pH calculation, I just forget step 2 because the common ion effect is going to mean that minimal hydronium is produced. Whereas, you know, for sulfuric it was like 10 to the minus 2, which is big. There's another acid in here in which step 2 will be significant. Let's take a look. Maybe something like citric? Well, the common ion effect citric is just like an order of magnitude difference between step 1 and step 2. So here, step 2 might play a role. Might have to worry about that. But it's still small. You know, we want a step 2 that's big, like 10 to the minus 2, 10 to the minus 1. If we have a 10 to the minus 2, 10 to the minus 1, for step 2, then we better worry about it. 10 to the minus 3, probably it's okay. Probably like HSO4, which has a 10 to the minus 2. And so when I say large K, I'm looking for 10 to the minus 1, 10 to the minus 2, maybe 10 to the minus 3. But for sure, these two are going to be significant. This saves a lot of time because you're doing a pH calculation. You know, you just look at the Ks and then you can determine if you need to do this. And so, if I was only interested in pH, I wouldn't have even bothered with step 2. I would have seen, oh, step 2 is 10 to the minus 8. We got the common ion effect. Forget it. It's barely going to contribute any hydronium. Okay, then, but I'm not interested in pH. Well, I'm interested in pH, but I'm interested in everything else in the solution. So we're going to do step 3. And so what's going to happen here is the hydronium is going to be carried down to step 3, and the monohydrogen phosphate goes down to step 3. And so step 3 is the next largest K. The next largest K is this one at 10 to the minus 13, just barely edging out water. Water is at 10 to the minus 14. And so we have HPO4, 2 minus, plus water. Going to produce hydronium, plus phosphate.
Even step 1 takes a lot of work.
Yes. This is why people look for tricks to save time. This is going to be 6.3 times 10 to the minus 8 molar. Hydronium, 0.0233 ... Phosphate, we assume nothing's happened yet. No collisions between monohydrogen phosphate. And so here we're going to lose a little bit, gain a little bit here. But because of the common ion effect, I don't expect to gain much. And so this is going to be 6.3 times 10 to the minus 8 minus x molar. This is going to be 0.0233 plus x molar, and this is going to be x molar. This is another trick that sometimes people use this. You know, in step 2, it always happens like this. You know, with the common ion effect and everything, that x is equal to K for step 2. See, because of the simplifying assumption. In step 3, it doesn't work like that. Some people try to say x is equal to K in step 3. No, it's not. You're going to have hydronium times the phosphate divided by the monohydrogen phosphate. So this is going to be 0.0233 plus x times x divided by 6.3 times 10 to the minus 8 minus x. And I just automatically do the simplifying assumption. This is going to be 0.0233. 0.0233 plus x is just going to be 0.0233. This is going to be times x. Now, the simplifying assumption is this. You know, I expect, well, 0.023 is kind of big. And so, but 6.3 times 10 to the minus 8 is not so big. And so what you could do is you could do simplifying assumption just to the numerator, but leave the denominator intact. You know? But we'll do it to both. Let's try it to both and see if it works. So this is going to be 6.3 times 10 to the minus 8 minus x. We'll just call it 6.3 times 10 to the minus 8, which means x is going to equal, because if we do it to both, that's less algebra that we have to deal with. And save ourselves some time. And the calculation is very quick. And so we don't waste a lot of time if it fails.
times 10 to the negative 18.
1.13 times 10 to the negative 18. Oh, then it worked.
That's really small.
It's a really small change, if that's correct. Is that what other people got? Yeah?
1.14.
Okay, 1.13 times 10 minus 18, which is going to be a very small percent change because the original, yeah, it's 10 to the minus 18 over 10 to the minus 8, so it's 10 to the minus 10 times 10 squared, 10 to the minus 8% change. Which is good. Oh, you know, did we double check this step 2? I forgot to do that. Yeah, otherwise we just wasted time on step 3. We should just double check to make sure we didn't make any simple mistakes. Somebody home? This is 6.3 times 10 to the negative 8.
All right.
So it works out. All right, so let's just
so it's significant. It doesn't even change it.
Yeah. So this is going to be 0.7063 minus. Now we need 17 zeros. Just rounded it back. Yeah.
6.3 times 10 to the negative 8.
Right. This is 8, whatever. Basically, this negligible change. We call this negligible change. It really doesn't have any impact on that. And the same thing here. It's going to be even more negligible change because, you know, this is going to come out to 0.0233 basically. And then X over here, phosphate. Here, is this negligible change too, the phosphate? No, it's significant. And so here we need this 1.13 times 10 to the minus 18 molar. Actually, this is the final concentration of phosphate. This is the final concentration of monohydrogen phosphate, but this is not the final concentration of hydronium. because,
Water back slow.
yeah, and so we're gonna bring this down to step 4. Our final step will be water. And if we think about water, water has a kW 10 to the minus 14, so we really shouldn't contribute anything, basically. But we're going to do it because water will contribute a little bit, and it'll contribute a significant amount of hydroxide to the solution. So even though this is an acid solution, there's hydroxide present because we can't stop the waters from colliding. So let's just figure out how much hydroxide. Acid solutions are just defined as having more hydronium than hydroxide. There's always hydroxide present from the collisions. So this is going to be 0.0233 ... molar, and then we're going to assume nothing's happened, so essentially it's reset left, and then we'll just do plus X molar, plus X molar. And again, the common ion effect is in play here, 0.0233 plus X molar and X molar. And so I'm going to get barely any hydronium, but anything significant compared to 0. And so this is the whole point in going this far, because the hydroxide will be significant, the hydronium insignificant.
You gotta bring down the step 4.
So, you know, this is kW, 1.0 times 10 to the minus 14, which is equal to 0.0233 ... plus X. And, you know, it's going to be slightly greater times X. And simplifying assumption should have no problem because we don't expect to generate, you know, there's a lot of hydronium here. We don't expect to generate much hydroxide. The population of hydroxide cannot grow too big. And so this is going to just be 0.0233 times X. And X is equal to times 10 to the negative 18, 13. Okay. This is kind of the weird thing that happens here in this particular calculation. That, you know, this had a K of 10 to the minus 13, that has a K of 10 to the minus 14. But when you look at the hydronium ion contribution, this has a 10 to the minus 18 molar hydronium ion conservation. But this has a 10 to the minus 13. So actually in step 4, we get even more hydronium than in step 3. It's weird.
Wait, so does it perturb?
Well, let's see. And so 0.0233 ... plus 0. I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros and a 4, 2, 9 here. Does it perturb?
No.
No. This is we call this a negligible contribution as well. Both of these would be negligible contributions. But here, for the hydroxide, it is significant, 4.29 times 10 to the minus 13. All right, so this is the final. Finally, we get the final hydronium. And so combining all 4 steps, the total amount of hydronium is this. And then the hydroxide is this here. And so this is what we can say about this. What we just did here is getting the inventory for phosphoric acid. And so if we have some phosphoric acid in a beaker, and this beaker, it's 0.100 molar phosphoric acid, that's what we mixed up, then because of the hydrolysis, you know, there are going to be multiple species present. And so let's look at all the species that are present. First, we're going to have H3PO4, the phosphoric acid molecules. This is 0.0767 molar. Okay, the next most abundant species, we're just going to go in descending order, will be hydronium. Yeah, hydronium is going to be 0.0233, slightly above. Right? The next species is going to be, dihydrogen phosphate, which is going to be slightly less than 0.02. Well, this was going to be 2999. Basically, it's going to be 2999. In other words, it's going to be about 0.023 molar, roughly. This is slightly lower, this is slightly greater. And then the next most abundant species will be HPO4, 2 minus at 6.3 times 10 to the negative 8 molar, followed by
PO4 3 minus.
no,
Oh, what? No, it's not.
hydroxide, followed by hydroxide. Hydroxide will be 4.29 times 10 to the minus 13 molar, followed by phosphate
1.13 times 10 to the negative 18.
times 10 to the negative 18. Do you see how the combined method is a total failure? The combined method says that, you know, the phosphoric acid is going to hydrolyze water to form phosphate. But look how much phosphate is actually present in this. Next to nothing. All right, and so what is the pH of this solution? So somebody take the negative log of 0.0233. Get the pH. 1.63. Give me one more digit.
160, that would change.
We don't want to round. You know,
It's 1.6326.
I want you to get in the habit of doing this. 1.6326.
26.
Okay. We don't want to round right off. Why? You always carry extra digits so you can double check your answers. And if you start rounding every answer, then you're going to have multiple round-offs here, which will give you. So you got to show me the round-off step here for all your calculations. All right, so that was phosphoric acid, just triprotic acid. Bit of work to do that, right? But all the acids are the same, whether it's a strong acid or a weak acid. We could do a diprotic acid, or we could do a monoprotic acid. Monoprotic acid is a lot easier because it's only Ka and Kw. Right? So in an effort to save time, I'm going to skip those. But I'm going to mention one thing. All the acids are going to work like this for polyprotic and monoprotic. You're going to do all the Kas first and then Kws at the end, because Kw is pretty small. Except for this one. If you're doing hydrosulfuric acid, H2S, you take a look at the second step here. So this one's weird because step 1 would be Ka1, step 2 would be not Ka2, step 2 would be Kw, because Kw should be a more significant, 10 to the minus 14, and then the last step will be Ka2. This last step should be the smallest contributor of hydronium. But otherwise, all the other acids should work, you know, on this chart here. It's just hydrosulfuric is unusual. So the acids all work in the same way. The thing about strong acids, though, is this. For a strong acid, maybe we should do that. Let's do strong acid like sulfuric acid. Show you. So the next example is we'll do 0.100 molar H2SO4. Now, Raheem?
Hi. Hi everybody. So I just want to make an announcement. I didn't make an announcement on Piazza, but I just want to let you guys know that this week is all chapter 16, right? So we went over chapter 16 on Thursday in great detail. We're not done yet though, so I hope you guys who were there are studying those notes. And we didn't get to do any practice problems, so something like this. Okay, polyprotic acids?
Yeah.
Okay, we're gonna go over polyprotic acids maybe either tomorrow or Thursday, depending on how fast we move over. Okay, but in general, Tuesday for sure we're gonna cover weak acids. We already started it, and we're gonna start doing problem solving with ice tables. Yeah, they're back. So hopefully I'll see you guys on Tuesday. And I'm still talking to the director for Wednesday workshops. So I'm gonna communicate with Shabao on that because I have to figure out what exact dates might the next at least 2 tests come on, and then I can decide. Okay, is it conducive to have a Wednesday workshop?
Well, probably next week we'll have chapter 16 on
Yeah.
Thursday.
Yeah, and I'm gonna let them know that right now.
Okay.
So I'll let you guys know. Hang in there. Good luck.
Thanks for anything.
Thanks for him.
You're welcome.
All right, let's do this one then. You know, for this one, Ka1 is very large. And then Ka2 is 0.011, which is 1.1 times 10 minus 2. So it's that we can consider pretty big. Kw is 1.0 times 10 minus 14. So as far as hydronium ion contributors, you know, when we had an acid solution, we look for all hydronium. So for sure, step 1, lots of hydronium. Step 2, because of the large K, there's going to be significant hydronium. Step 3, do you expect much hydronium? And so if I were doing pH calculation for this, I'd do step 1 and step 2 and ignore step 3. Because step 3 is barely going to contribute any hydronium. Okay, so let's go with step 1, H2SO4 plus water.
So for the last one, would you still have to do it if you wanted to see the OH?
Yeah. Yeah, we're going to do it because we want to see everything. So we're going to get hydronium plus HSO4 minus. That. You start off assuming everything's reset, so nothing has taken place.
But you're not resetting it, no?
Huh?
You're not resetting it.
Well,
He hasn't started.
we haven't started. You know, reset is just, you know, we always start our acids and bases 100% on the left.
Okay.
But in reality, these have already equilibrated. If I have a beaker that's labeled 0.100 molar H2SO4, then it's already happened. Everything has already happened, right? And so what I'm doing is I'm trying to reverse time and then pretend nothing's happened, right? And then just let it collide. But for this one, when we have a K that's very large, then it's like Chem 1A stoichiometry. We just look for the limiting reagent, and water is going to be in excess. This is a limiting reagent here. The limiting reagent is completely consumed, so we go to 0. And then it's all 1 to 1 to 1, so it's going to be 0.100 molar hydronium and 0.100 molar. You know, complete. We say complete reaction. In other words, strong acids are 100% ionized. So it's 100% ionized. It's kind of funny because let's just do a quick aside here. It doesn't matter what the concentration of the acid is. You know, if I look at the percent ionization, whether it's, you know, highly concentrated or highly dilute, it's going to be 100% ionized. This is strong acid. But if you remember back in chapter 15, could we use percent reaction as a way to predict the stoichiometry of the equilibrium reactions? We tried it actually. Remember the first reaction we looked at, we tried to look at the percent reaction. The percent reactions were all over the place, right? And so for strong acids, we don't do an equilibrium calculation. This is just complete reaction here. But for weak acids, this is the way it works. For weak acids, I said that acetic acid was about 0.1% ionized. But I can't give you a strong number for that because it depends on the initial concentration. the percent ionization changes. Otherwise, we could predict all these just by looking at the percent reaction. That would make these ice calculations so much easier. If all acetic acid samples have 0.1% ionization, then we're done, right? But it depends on the initial concentration, it depends on how much common ion you have. The amount of common ion is going to decrease the percent ionization. And so when we look at this, for weak acids, the percent ionization is not a constant.
What if you have glacial acetic acid?
Glacial acetic acid is as pure as you can get. And so the percent ionization of glacial acetic acid is totally different than the percent ionization of vinegar. And so typically glacial acetic acid is going to have a lower percent ionization than vinegar, because the way it works is this: as the concentration of the weak acid gets stronger or higher and higher, the percent ionization gets lower and lower. As the concentration of the acid decreases, as we get close to zero, the percent ionization goes way up. And so for weak acids, the percent ionization is not fixed, it changes. So this is for weak acid. But for strong acids, it's easy because strong acids are always 100% ionized, so we don't have to think. And it's easy to predict the stoichiometry. If we know the percent reaction, then it's easy. It'd be 100% reaction. All right, so what we're going to do is we're going to carry this down into step 2 and carry this down into step 2. So we're going to have HSO4 minus plus H2O liquid. This is going to give us hydronium plus sulfate. So from step 1, we have 0.100 molar HSO4 minus and 0.100 molar hydronium. And again, we assume nothing's happened yet in step 2. Here, this is this K is 0.011, so we don't know. It's not 100%, and so we'll just call it minus X, plus X, and plus X. So we're going to get 0.100 minus X, 0.100 plus X, and X. When we go over here, this is going to be 0.100 plus X times X over 0.100 minus X. Now the trick here is this. The trick is that, in step 2, X is usually equal to K, if we use the simplifying assumption. If we use the simplifying assumption, then X is just equal to K because these two terms cancel each other out. But looking at that, this is a fail. Some people like to memorize these little rules, but they don't like to memorize the exceptions. Little rules. Unfortunately, this is a fail because it turns out it's going to be 11% change. 11% change is too big, right? And so, we can't use the simplifying assumption for this. What we have to do is we have to use the quadratic or successive approximations. Which one do you want to do?
Successive approximation. Wait, no, quadratic seems easier.
I don't know.
How is that 11%?
Is it 11%?
X equals 0.1 more.
Oh, well, X would be equal 0.011.
Yeah, over.
And
0.100.
Over the initial 0.100. 11%, which is too big. Well, anyway, we'll go ahead and do this. So this would be 0.011 times 0.1, which moves the decimal to 0.0011, right? So we get 0.0011 minus 0.011x is equal to 0.100x plus x squared. And so let's get this in quadratic form. X squared, we'll add this to both sides. So x squared plus 0.111x minus 0.0011 is equal to 0. Did I do that right? And then I'll go to, for your homework, you can always bring up a web page or whatever and with a quadratic equation solver, because you have to solve a lot of quadratics, unfortunately. Oh, 0.111. 0.111, and then the last term is negative 0.011.
Sir, I think you forgot to combine the 0.100x and the. Oh, I see what you did. I did it backwards, I'm sorry. Yeah.
Is it right?
Yes.
Okay. All right, so I get two roots. One of these is negative, which doesn't make any sense, and the other one is okay, 0.0091. So I got x is equal to 0.00915. All right, so I go over here and I go 0.100 minus 0.00915. So we need two extra zeros. This is going to give me 5, 8, 0.
Excuse me, if we plug in that negative root, do you get a positive answer?
No. Oh, if we did it here, yes. But what about here?
No.
And here? No, but if we plugged in negative, we'd still get a positive here, but this would come out negative, which is impossible. We can't have negative atoms, negative grams of atoms. Well, anyway, you get this. And so this is about 10% ionized, in step 2. Then over here, the hydronium, this was a significant contribution of additional hydronium, because here we're going to have about 10% more hydronium, 915. So we're going to end up with 0.10915. And the sulfate, 0.00915. Well, let's double check this. Does the case still check out? It's supposed to be 0.011. What did you get? You have 0.011? All right.
0.01.
Well, you give me the numbers. Don't round it off until 0.109.
0.01099.
Okay, 0.01099, which checks out. Just round it in our head. But you notice something. Did this perturb step 1? Because what we see is a significant change here. There's a significant change. This is not a negligible change. Significant, not negligible. Like in the previous example, is negligible change. Must we solve this simultaneously?
Where's step 1?
It messed up step 1. Must we solve this simultaneously? Must we solve this simultaneously?
Wait, take a significant change?
Because now step 2 is in equilibrium, but all the concentrations have changed for step 1. So now step 1 all screwed up. Yeah, definitely. I mean, it was originally 0.100, now it's 0.09. This was originally 0.100, now it's 0.109. So it's about 9% change, right?
But how is it significant?
9% is significant. If it were like a 10 to the minus 8% change, then not significant. But a 9% change is significant. Let's say, your bank account. If you lost 9% of your bank balance, is that a significant?
Yes.
Yeah, but if you lost 10 to the minus 18%, maybe it's not so significant depending on how much money you have. But
Wait, so you're comparing that number to the initial? That number to the initial?
Anyway, yeah, this is a significant change, wouldn't you say? 9% is a significant change. So did that screw up step one? The answer is no. Why?
What?
Oh, because the step 2 was
No, step two is significant. Step two is significant. It should perturb step one. It does perturb step one. But do we need to solve this simultaneously? Step one never changes. Step one never changes because it's a one-way reaction. No matter how much you put in here, Le Chatelier's does not perturb one-way reaction. And so the answer is no. Le Chatelier's is not going to screw up. The reason is because K is very large. K is very large for step one. And so we don't have to worry about any kind of perturbation when K's are very large. Okay, I'm going to stop here.